I think he was supposed to prepare for you like a summary of all the Keldysh formulas. He was a bit busy, so it's going to arrive by afternoon. So you're gonna get it. It's just a little bit later.
I think if you check your email.
Is it already there?
I think I got some email.
Yeah.
Then maybe he already has it, like because then he. So maybe he managed. But I mean, I'm sure that by now you're already specialist in Keldysh, so you don't even know that, right? And you know, and over this past 3 days, you learn how to, now you know how to take your favorite Hamiltonian in second quantization, and you know how to express it in terms of time-dependent fields on this closed time contour, right? And why do we like this closed time contour? Because the only input data that we have there is the initial state. And in principle, we can study the time dependence of the fields, right? And this is very different than, for example, the path integral approach to scattering theory. Maybe some of you took like some high energy particle physics course when they do path integrals and compute amplitudes of processes. Anyone has seen amplitudes in their life? Maybe vaguely, I mean, no detailed knowledge necessary, but you know what they are doing there, they have their path integrals on a straight line, right? Like they don't play around with this like closed time contour. But the problem there is that to compute any of the probabilities of processes, you need an in state and an out state. So you already have to know what the outcome is, right? To compute the amplitude, to compute the probability. So why are we playing with this whole complication with a closed time contour? Because we don't know what's the out state yet. We want to discover it via studying the time evolution. Okay, but now we need a method how to extract the dynamics out of this Keldysh contour, okay? So there are many ways how you can actually study the Keldysh action. But for the methods to be, let's say, useful for really studying dynamical systems, you would like to care about two properties, secularity and universality. And let me give you an example, for example, why perturbation theory is not great for that. When you do perturbative expansions in some small parameter, in some early times, it's all good. You have, every term in the expansion is smaller and smaller, but they start growing in time. So, and this is the so-called secular terms, the ones which explode. So very quickly, your perturbative expansion is not perturbative anymore. And how are you supposed to study in dynamics, right? And the other point is that you want is the universality. You want, in principle, your system to thermalize. You don't want to put thermalization by hand. So you want your description to lead you to some thermal state, which is universal, meaning it does not depend on the details of the initial state. And the problem, for example, with a lot of methods, for example, like Hartree-Fock approximation, the problem is that they generate some fictitious conservation laws, and actually the steady state is not the actual steady state of the theory, it's just some fake steady state made by approximation. Okay? So today we're going to talk about the NPI approach to extracting dynamics out of the Keldysh action, which is supposed to help us with these two problems. So this is a sort of this functional integral approach based on an n-particle irreducible effective action. And why is it n-particle irreducible? You're going to see it within the construction, okay? It's really not obvious from the beginning. But the point is that the n-particle irreducible action, as building blocks, it has endpoint functions. And because they are the intrinsic building blocks of this action, it preserves the symmetry of these functions. But I said n-particle. Okay, n-particles is often a little bit many particles, okay? Not great, not very practical. So in practice, actually, it turns out we already gain a lot by actually looking only at two-particle irreducible. That it's already, because what is a two-particle correlation function? Is the propagator. Right? So already having the propagator, the full propagator as a building block of your construction is already a massive gain. So today we're going to talk about the 2PI, so this two-particle irreducible formalism. But at the same time, both these 2pi expansions, perturbative expansions, in principle, they have nothing to do with Keldysh. They're just a way of approximating things. So for a second, we're going to set aside field theory and look at a very simple example, which has nothing to do with field theory, and to compare perturbation theory and the NPI type expansions. So we're going to look at some damped harmonic oscillator. Yeah. You have a series of all these higher order terms, and this in principle can be summed up as a geometric series. You can plug it on a computer and solve it numerically. What do you expect is going to be dynamics of Y? What sort of graph you expect? Exactly, oscillator, but with time is going to be damped, right? So we want something like, okay, so this should be our exact solution. But now let's say we want to compare the exact solution against some approximations. So is this visible? I think it is. Okay, so first, perturbation theory. So in perturbation theory, we would start from writing a perturbative ansatz, which is basically some Taylor expansion around the non-perturbed solution. Yeah. Make sense? So I plug it in, right? And then after plugging it in and compare order by order in my small parameter epsilon, what do I have? So I get some tower of differential equations I need to solve. Let's say they're not particularly difficult to be solved. So we see at the first order, this is just harmonic oscillator, right? So I recover sort of some mean field solution of just oscillator, and then I'm adding more and more damping. And what it gives me, at the end of the day, that the perturbative solution up to order epsilon squared is going to be something like this. Is my writing clear, or anyone? You can read, yeah, good.
Sorry,
Plus complex conjugate, where's that? I'm gonna do it. Okay. These guys? Yeah. So this comes from, I plugged this guy into here. So my every y becomes this y perturbative. And I'm going to have, so on this side, for example, I'm going to have, okay, second derivative of these guys plus just these guys. But here, they're going to be like, for example, multiplied by epsilon. So I see that if I want to, and I'm saying, okay, so these are the terms order epsilon to 0. These are the terms order epsilon to the first, and so on. So you see on the first order, for example, here there will be no terms epsilon 0 because everything is multiplied by epsilon, right? So that's why I get this guy. And the mixing comes from the fact like, okay, when I plug it in, going to be epsilon times y0 in the term with the derivative, right? Further questions? Okay, so this is the solution. Why shouldn't you like it?
Because it's not an harmonic oscillator. You are growing time. You have the secular term.
Exactly, the secular term, so the growing in time bit, this is the problem, right? This is supposed to be a perturbative expansion. But look at this guy. And I mean, also, you know, here. This very quickly, it's definitely not going to be a small term. So this sort of expansion is valid only for epsilon t, and this is a bit of a for smaller than 1.
More.
Yeah, maybe this one's a bit weak, right? Which is not very useful if you want to actually study dynamics, right? I mean, if you want to study just, you know, how things just after, you know, some quench behave, sure. But very quickly, it's not going to work. So there's another idea, and this is going to be like somehow like a truncation in the style of this n-particle irreducible truncation. So what we do, we don't make an perturbative ansatz. Directly at the level of the equation, we do our order of approximation is a truncation. Do we have it? Perfect. Is considering the terms which are of a particular order in epsilon, but already here. So my 0th order approximation, I'm cutting off here. I'm just having a 0 here. 1st order approximation, I take only this guy. 2nd order approximation, there's no epsilon to the second. So 2nd order approximation is still here. 3rd order approximation, the same as 4th, and so on and so forth. Okay? So now is our NPI. So at the 0th order, this is my 0th order approximation. I get just harmonic oscillator, right? And this agrees with perturbation theory. So the mean field solution, great, both sort of schemes give us the same result. But now let's look at the first, which is also the 2nd order approximation. This guy, the solution is going to be and I mean, this is sort of not a hard equation to solve. It's going to be an exponential. Yes. Sorry?
1st order term.
Only because in this particular example, the 1st order approximation and the 2nd order, they're the same thing because there's no term epsilon squared. So that's why I sort of, you know, I could have called it y1 and it's the same stuff. Okay, so what do you immediately notice about this guy?
The argument of the square root can be negative about some point of t.
Sure, but do we like that?
We like that because the exponential will decay.
Exactly. So we want that. We want it from, you know, from our computation. I mean, here we are missing that as the mean field, right? So we want to have some decay on top of it, but also this guy is going to be bounded. Okay, it's not going to have all these exploding terms because actually it has, if I expand this exponential, what I'm gonna get is exactly this plus loads of higher order terms. Okay, there's gonna be epsilon cubed, 4, 5th, and everything. So inside of this exponential, there's some infinite resummation of these higher order terms, but this infinite resummation makes sure that my order is bounded, that I have no secular terms, and give sort of the strength of this approach, okay? In principle, doing it by hand, I wouldn't know what to add here to make sure that my error is bounded. Here, it's taken care of automatically.
So can you explicitly mark the expansion there, the terms that you keep to determine?
Yeah.
Okay.
Yeah, exactly. So this guy, y equals to the y p of t with the second order plus terms of order epsilon cube and higher. So up to the terms in epsilon squared, they agree exactly if I expand the exponential. You can check it, exercise for the audience. But then I have all these higher order terms, and of course, this is infinite Taylor series in principle, right?
Sorry, probably something that you said,
Yeah.
but my question is, suppose that I arrive with the full expression of the perturbative series, and then you want to reconstruct Y2. Do you have a rule to decide which term you keep and which term you don't keep? You see what I mean?
I don't.
Okay.
I would assume it very, maybe for some simple systems when you have like some good physical intuition. I never tried. So, but I would assume it would be very difficult.
Because
Yeah.
again, probably because
Yeah.
I missed the exact moment that was relevant. What is the rationale there? You say, okay, I take of the equation only the part that is up to quadratic in epsilon, and then I solve it exactly.
Yeah.
This is your rationale. See. Yeah, I don't see immediately how to reconstruct this
So-
summation.
And I think it's not obvious because in a way this is also, so at infinite order, everything should be agree, right? Like if you sum it up to infinity. But the thing is, this is sort of like a cell of
Exactly.
that guy, right? So this is also truncated.
Exactly.
And that's why I think it's almost, I wouldn't say any way of doing it by hand from perturbative expansion.
Those another thing. That
Yeah.
is a series that has a finite radius of convergence, I guess, right? Yes. In case your series is asymptotic, is still usable, this MPI, or?
In case I don't have a problem with
No,
sequators.
this is the opposite. Suppose that is asymptotic, so the radius of convergence goes to 0.
Yeah,
Still, you can do the MPI and get meaningful results.
I would say so, yeah. Yeah. Yeah, so here, like this guy has an error of the order epsilon 0, I think, for all times. Okay. So this was like sort of like just an example on some simpler differential equation. Now coming back to field theory. Okay? And why we are happy about, we want to use this 2PI approach. Now we are not doing all the NPI, 2PI approach. Actually, this was also just the 2PI because I didn't go to any higher orders. Why do we want to use it on field theory? Because in principle, what we expand in, yep, go for it.
Plastic.
Yeah.
From this, should I see the origin of the name to PI, or for the moment it's just no, right?
I think here I don't see it.
Okay. Please. Go ahead.
Yeah. Yeah, because it's a more visible
Exactly.
in field theory. It makes sense because it's diagrammatic, right thing. Yeah.
But this equation is kind of like more theory. If you just forget. Also, if you sum everything, you're going to have epsilon cubed.
Yeah, because it's odd power, so it's what, like
You-
sine Gordon interaction, I know.
But maybe for a small y, you can have like a 5.2. Because if you sum everything, you're going to have
Even like this guy.
Yeah.
Yeah, but then there's the 5-4 would be without this guy, right?
oh yeah, you have the velocity. thing,
Yeah.
So yeah, it's not a 5.4.
I mean, but you can do 2pi on 5.4, but then, you know, just going through the field theory route. All right, but what you notice here, we still have this epsilon, I assumed is a small parameter. Right? Which the nice thing about 2pi is I can actually choose other parameters to expand in. I do not have to use small coupling. So, for example, I can use h bar to do an expansion by taking like my sort of stationary solution is a classical solution of a theory, and then higher order corrections or quantum corrections because they are in h bar. And in this way, I can have actually strong coupling that I consider in my theory. And that's already a big plus that I can consider strongly coupled systems. And on top of that, although, you know, 2pi is still an approximation, we still, you know, we do some diagrammatic loop expansion, we still truncate it. But because of this hidden infinite resummation, which is implicit in case of the field theory is going to be implicit in a full propagator, this expansion is going to be self-consistent, and also no symmetries of the propagator are going to be broken by this truncation. Because the full propagator is going to be our main building block of the entire construction. Good. So now we can actually go to calculating something. Maybe I'll remove this first. Yeah. So you remember you had your Keldysh contour. Minus, plus this guy, it's minus C plus, and the entire contour is C minus plus C plus. And this is our time, okay? And now if you want to actually compute a partition function of any system of interest, right, is a standard that we have the time evolution propagator times the initial state. So what it means, I plug in here ρ0, and then this is the time evolution and parameterized by this contour. And you saw in this Keldysh, all these Keldysh construction exercises, that now this guy, and I'm going to concentrate on the Hermitian system. So we're going back to Hamiltonians just to make things simpler. This guy is some e to the minus I h L C. But now we split it into infinitesimal guys in between our resolutions of identity, right? And then, and so on and so forth. And this is in this way, and that's what we know. I mean, it's a very rough sketch, so I hope it makes sense from the previous days. We get the partition function, right? You insert your resolution in terms of coherent states. You act with second quantized operators on coherent states, and you get fields out of it. And as a result, you get some path integral of an action. So that is what you already have seen. But today we're going to start from this point that we already know how to put a Hamiltonian on a Keldysh contour and go further. We're going to start with the simplest model I could think of. namely the anharmonic oscillator. I think yesterday during the tutorial, you did some exercises on the anharmonic oscillator, right? And these guys are operators. Do you recognize that this is also a harmonic oscillator? So rather than working with creation elation operators, I'm going to the basis of coordinates and conjugate momenta. Why? Just because the construction is easier with real fields. So why would I complicate my life by using complex ones? Okay, just keep it simple, just to see the essence of the mechanism. So how do I get Lagrangian out of a Hamiltonian?
T minus B. So your potential is gonna be the last part of the, because this Hamiltonian is quadratic and you don't have mixtures in the thing, so just change signs.
Almost, right? Between Hamiltonian and Lagrangian, we have Legendere transform,
Yeah.
right?
Yeah.
Which is, maybe you saw, it's like this. L is like some PQ dot minus H. In this case,
Yeah.
it's P X dot, right? Minus our H. And this guy is going to give us our action. And implicitly under this arrow is all that you've done the previous days, putting it, inserting identity and putting it on the contour. The action is in terms of now field X, not the operator X. It's integrated over time on the parameterized by the contour. This guy. But now tell me, what sort of resolution of identity did I need to plug in on the contour to get these fields? Would coherent states work? Right, exactly. I need a resolution in terms of some states, which are eigenstates of the X operator. But I can do it. Nothing prevents me from doing that, right? So if you're encountering the coherent states basis, it's useful when I have creation and annihilation operators. But if I have some other operators, I just insert different resolution of identity and proceed exactly the same. Right? Easy. Well, just so you don't get scared that there are other operators. Good. Okay. Okay. Sorry, if there's angels, you can change marker to a newer one. Yes. Absolutely. Okay, this one is bad. I think maybe this one is gonna be okay. Check this guy. Oh, this one is better. Okay. Perfect. Good. So now, usually what we do with path integrals, we need some generating functional. And this, if you haven't seen it before, that's fine. But how generating functional looks like is something which looks similar, like our partition function. But now I have additional, so this is my function. I have additional so-called source terms. What's the use of the source terms? Does anyone know?
To one collision function average.
Eventually to
help with the derivative of the.
Exactly. They're basically
Basically
these
what-
non-dynamic objects we introduce. They don't take part in dynamics, which allow us a handle on the fields. And by a handle, I mean now I can differentiate with respect to J. This is going to pull X down from the exponential. If I have X here, This is going to be like an expectation value, right? And I can set J to 0 because it's already served its purpose.
So your second derivative is gonna be like your second couplet, something like this. Like the first one gives you the average, the second one gives you the second momentum.
Yeah, actually, yes. Okay. If I did, in terms of perturbation theory, yes, this is how you do it.
Oh, it's okay. So
Because the difference is, so usually actually, what maybe if you've ever seen, you know, sort of linear path integral scattering theory, people just write this. Because I want to pull fields one by one down and perturbatively create higher and higher point correlations. But, and this is where the sort of the 2pi difference turns out, we add additional term. We add a 2-point source.
So can you help us to understand the machinery of adding these terms? Like how, looking to a problem, we can just, okay, the source terms that I'm gonna add is like this. So you are stopping in this kind of 2-point function because you want just to go to the second point.
So I'm stopping at the 2-point function because I want, so in principle, right, I can go to endpoint sources, not
Yeah.
practical. Why I go beyond 1-point source? Because I want my 2-point function, so the propagator, be the building block of a theory. So this source basically makes, okay, my single point function is the building block of a theory. Now I extend it to both the single point and the 2-point function is going to be a building block of a theory. If I go to higher point functions, I sort of promote them to my fundamental objects within my calculations.
Okay.
For me, I would in the propagators in the action, right? That's terms.
Yeah, exactly. But this is the paired propagator. It's in the action. And also what we want. The information about the propagator is within the action, but to actually compute its expectation value, we want, so what is an expectation value? Expectation value is something like 1/z because normalization and average of the operator, right? Agree? We need to bring this guy down.
Yeah.
And how do we bring it down? By using this non-dynamical functionals that eventually we need to, they cannot affect the physics.
Yeah, on the language of probabilities, like you have your distribution given by Z, and then you build a function generator of momentum.
Yeah, I guess so. Yeah.
And you just, because you can write your probability distribution as the sum of all your momentum. So it's like a Taylor expansion for probability functions. So
I think I got a bit lost, but maybe.
I think that why you read something like this.
In probability, you would call it a characteristic function.
Yeah.
Good. If it helps someone to understand, that's great. Any further questions about that? You can also just for now trust me that this is gonna produce something nice. Okay. Good. Okay, so now we want to generate these expectation values. Because we want to normalize.
There is a question of shadows.
Oh, yeah. Could you also obtain a 2-point function? Oh,
The second derivative of J.
with respect to J twice. Exactly, you can, but that would mean that your 2-point function is
Thank you.
that your 2-point function is generated in a way perturbatively. So it's not a fundamental object in your theory, is generated only via renormalization of your one-point function, which is stuff people do, right? For example, in perturbation theory, in scattering theory, great. I mean, even with Keldysh, you can do that. But we would like to take care also of the symmetries of the propagator.
I have another question.
Yeah.
What is your like your parameter of expansion in your function out there? Because maybe
There's no expansion yet.
but you truncated it. Like I just want to do the building.
For now, there's no truncation.
No.
There's no truncation yet. So we talk about truncation when we actually truncate physical degrees of freedom.
Okay.
These guys, they are just point terms, okay? So it doesn't matter however many I put in, I just use them as a tool, but they have no fundamental meaning. So in this sense, I just, put 2 of them. I could put 3. Great, right?
At some point you want to compare your theory with the exact solution. So then
I mean, there's no exact solution to interacting.
The moment that is the exact
I mean,
solution.
For now, it's
Yeah.
exact.
so you can
Yeah.
compare something with your exact solution and then see that, oh, stopping this term, I'm gonna have an error like this.
This is, okay, these terms are just tools which help us with truncation of the grammatic expansion. And this is where approximation comes in. But in principle, whether I add only 1-point term, 2-point term, n-point terms, this is still the exact theory. So if I never truncated anything, I'll get exactly the same result, both with 1-point functions, with 2-point functions, 3-point functions.
X to R X.
Sorry? I don't hear you.
R X terms.
Why did I put the 2-point?
I can see the J purpose.
Yeah.
Right, you take derivatives as well.
Yeah.
But this term that I can just explain why.
I think you're gonna see it later.
Okay.
I think for now you need to trust me.
Yeah.
And to trust me, I'm gonna complicate things a little bit more so that they become better later, okay? Good, so generating expectation values. So we define this function because we want normalized expectation values, right? So now it gives me 1/z derivative of z. And I get my derivatives with respect to sources. With respect to j, what do I get?
1/z, the average.
I mean, it's actually going to be the average, right? 1/z is included because this is just a normalization,
Oh, yeah, of course.
right? In case my path integral just over here is not normalized already. So we're going to call it some x average. And now what happens if I differentiate with respect to the other source?
The 2-point function. X1, T1, X1.
Okay, but this is going to be this is a full correlator. So what can I do with a full correlator?
You can subtract the classical part.
I can put it in terms of, so it's going
The
to be
connected correlate.
equal to my 1-point expectation values plus the connected part. So, and what are these guys? X, T1, X, T2, right? So it's the definition from the previous one. And this we're gonna call G, T2, T1, which is very suggestive. This is gonna be our Green's function. Okay?
I didn't quite get that last step.
This guy?
Yes.
This is just a statement of This is just a statement of Week's theorem. So in a way, it's the definition. I don't think I have a better explanation that inside a full correlation function of two operators, there is some part which depends on really truly connection, the correlation between these two guys, but also there is a hidden part which depends only on the product of expectation values.
And then that whole there, it means what exactly? It means that it's not an average that lasts determines.
No, this means that it's just a connected part, and by connected, we refer to connected as the bit which is really truly correlated without contribution of these guys.
Now I understand.
It's like the quantum variance when you subtract the several parts.
Yeah. More questions? Okay. I don't know whether you're silent because you're terrified or because it's so trivial or a bit of both. Okay, good. So now we have this guy W, which is, and both of these guys W, Z, they're in terms of these non-dynamical source terms. But we would like a description of our theory in terms of actual dynamical degrees of freedom. And what are our dynamical degrees of freedom? And maybe I need a different color. This guy is our degree of freedom of interest. This guy is our degree of freedom of interest. So what do? We want to make a change of variables. We do Legendere transform. Okay, the same stuff as going between Hamiltonian and Lagrangian description. They contain the same information, just different variables. We're going to do the same here, okay? So instead of generating things from W, which is in terms of J and R, we want Legendere transform of these conjugate variables. So J is a conjugate variable with respect to this guy, and R with respect to this entire guy. Okay, so now I have this yet other object I'm defining, and this is actually going to be my gamma 2pi, my 2pi effective action, okay, which is completely not clear why is it called 2pi at the moment, okay? So again, you have to bear with me with the nomenclature. This guy is going to be in terms of my dynamical degrees of freedom, and so the Legendere transform of W with respect to, so now the source, and what's the conjugate variable?
Bar.
X bar. Right? And that's the difference between this and what was before. And minus dt1, dt2, r1, d2. And now is going to be x bar t1, x bar t2 plus g t2 t1.
So
Um,
can I-
yeah.
just to refresh, we have this action, and then we are computing things with this action. And then we have the functions of interest. We have X bar and we have G.
Exactly.
So the Legendere transformation that we are doing is just to compute things as a function of X bar and G.
Exactly. There's nothing happened, just a change of variables happened to the ones we were interested in.
Just to erase the parts, the variables that we don't want. We don't want to compute our 2-point function as a function of X bar. So we are doing a transformation to write our 2-point function.
Exactly. We want an object which some generate, some action which has the two objects we're interested in, right? The Green's function and the 1 point exploitation value.
I guess because then you will do some sort of saddle point analysis or something.
Precisely. To do corrections on top of the saddle point. And this is, you're already anticipating my next step. Because in fact, okay, staring at this is also not particularly nice expression, right? Like when I plug in W, actually it's not immediately obvious how J and R disappears. So what we're gonna do now is a little bit of a massaging of this expression to have a nicer form, okay? But first, we're going to do it the saddle point approximation. So we're gonna think about our field X. We're gonna express it as some saddle point solution, so my average, times fluctuations around it. Right?
So H plus.
A plus, of course. There's fluctuations around it, right? So we can study we can study this guy, but we also can have some corrections to the saddle point solution, where these corrections are gonna be with respect, we're gonna do it with respect to as quantum fluctuations, because we're gonna expand in H bar. Okay? So now there's a whole game of, I have this, and I need to plug into this massive expression and not go crazy on the way. So we're gonna attempt that feat. And we'll see how it goes. Okay, so let's first plug in this guy into Z. What I'm going to get, my ZJR, it doesn't make sense I'm plugging it into Z because Z goes into W and W goes here, right? So sort of, a couple of steps. Z. So I have my exponential. So I'm plugging this into my action. I'm going to have, and I'm not going to write it explicitly, I'm going to have part of the action, just my classical action, which depends only on the averages. And I'm going to have part of the action, which I'm going to call S fluctuations, which depends on both the averages, but also the fluctuations. And on top of that, I'm going to have, and I'm going to write it in a shorthand notation without the integrals, so it's a bit easier. I'm going to have terms of the form I, J, X bar, I, J, phi, my fluctuations, I, R, X bar, plus 2 I phi or X bar plus I R phi. Yeah, I literally just plugged into the generating function now. So now what happens? There are terms. We're under the path integral, but then now we have a change of variables. Right? We have a change of variables from this guy to this guy. This term, and this term do not depend on the variable which we're integrating. So we can take it out. So the exponentials of these terms go out of the integral. And then when I compute W and take a logarithm, they just come down. Okay? So I get W being as, and this is visible, okay, as classical plus the term Jx bar plus the term R X bar minus I logarithm the rest of this stuff. Okay, and I'm going to add, and this is still under path integral, and I'm going to call the rest of this stuff delta S. Okay, so this is the W. But my gamma to pi is W minus these guys. So you immediately see this guy is going to cancel with this one. This guy cancels with this one. And what I'm left with more space. So what I'm left with is that my gamma to pi is the classical action minus I logarithm of this leftover bits of action minus trace RG. How did I get trace RG? Where did it come from?
From the Legendere.
Which term was left apart from the action terms?
The left, this, yes. This integral is,
Why do I say it's traced? Right, so this is the trace in time indices. T2, T2, T1, T1. That's why it became this guy.
okay.
Yeah? Very good.
I have a question.
Yep.
This is kind of like a Feynman-Vernal,
Sorry.
Feynman-Vernal theory, like of effective action. I don't know if you compare it.
Oh gosh, no, I don't think I know this theory. So I'm afraid I cannot help you with this one. Do you know this theory?
You mean the influence functional or Feynman-Vernal influence functional or?
Feynman-Vernal theory, anticipation, they also use on classical action and an active action where it would on anticipation. So
Yes, this is, I think it's. I believe it's a bit different from that, but I mean, let's say that the idea is in both cases that, yeah, you have, let's say, a background and you have fun about it. And then let's say you do, you do your thing.
okay,
But yeah.
okay.
Yeah, but let's say, saddle point approximation is also not a unique thing to either to 2PI or even quantum field theory, right? Like it's, in a way, is a rather standard thing one can do even when computing, like, Heisenberg equation of motion, you can, try to also expand around some mean field solution. Exactly.
So you just take the maximum point,
Yeah.
like very sharp peak, then you can take just the maximum point for approximation.
Exactly. So this is sort of, something which is used broadly, and we make use of it here as well.
I have another one.
Yeah.
You're assuming lambda on your potential, and it's positive. Where you make no assumption.
I think they make no assumption, but
They're very different, right? If it's positive or if it's negative.
I don't see where I would need lambda to be positive in this case. Like for now, the positivity of this part of the action didn't enter. Maybe at some point it does enter and I missed it, but for now it doesn't. So not yet, maybe in the future. Okay. Good. And now, so what do we do with them? We still need to do something with this guy. So what is this guy going to contain? It's going to contain some, so delta S is going to be some delta S linear in terms of fluctuations, plus S quadratic in terms of fluctuations, plus something I'm gonna call SV. So this is gonna be cubic and quartic in terms of fluctuations. So my interaction term. This guy is going to involve J. We're going to implicitly assume that we adjust whatever J is, we don't care what it is, but whatever it is, it always cancels out these contributions. Okay? Again, Weber standard, because we have these additional degrees of freedom, we can adjust them however we want, as long as it's consistent with the theory. So we can choose to adjust J such that it cancels out the 1-point functions. So in the following, I'm just going to ignore it because this is taken care of by J. So I'm left with these two guys.
I think that is some-
Oh, yeah. But can you repeat the last one? I can't see the subscript. Superscript of the yeah. The superscript was 1, meaning that it's linear in fluctuations. 2, quadratic in fluctuations. And here I put V because it's just higher order in fluctuations. Actually, it's going to be 3rd and 4th order in fluctuations. I hope that helps. Good. So now I want to remove action at the board is too small for me. Actions, maybe we'll keep it. And now I want to deal with this term because it's not particularly nice. So I can expand it minus I logarithm. And now I'm not doing anything. I'm just multiplying by identity. As this is the quadratic guy. Here on top, we have a quadratic plus higher order guy together over as 2. Okay. Now this is a logarithm. So what can I do? I'm gonna be cheeky. That is 2. I can do it like this plus logarithm of this. Right? This is a quadratic of integral I can solve. And what is this guy? How does it look like? It looks like an average, exactly. It looks like an average of my interactions with respect to quadratic action, which is already something we like, right? Because the most quadratic action, we can do Wick's theorem and everything, and the world is a nicer place. So this guy, this is going to be the expectation value. This guy is going to become an expectation value of is the I delta interaction and my gamma, and at this stage, my gamma to pi is the classical action minus this guy, this quadratic guy. For now, plus this expectation value, but these are higher order terms. In fact, in something in a parameter we're expanding in. So I'm saying for now, higher order terms. I'm gonna ignore it for now and concentrate on the saddle point of the action. Okay? And here, which you said, I think, already before, has the point of we have the propagator inside the action. Cause, so what is this guy? This guy, this delta S2. Then I'm running out of board. Delta S2, this quadratic guy is going to be and this came up only because of plugging in our expansion, right? Like T plus see here. Quadratic guy. I can write it as I don't mix up my words. I can write it actually as like there's some factors of I floating around, but you have to trust me on that. I can write it as phi, some operator phi, right? Quadratic and phi. And what's going to be the operator is going to be inverse of a Baire propagator minus IR. Factors of I floating around they're correct in the notes you should get. So R comes from here. Why am I saying, so G0 inverse is this guy. Why am I saying this is the Baire propagator inverse? Because this guy is the same as this guy of P prime is the same as now taking the full action, the guy in the blue border, derivative with respect to functional derivative, P prime, evaluated at the saddle point. This is just a matter of plugging in the numbers, but this is what we're talking about. Like, okay, why can't I just differentiate with respect to 1-point field? This gives me the Baire propagator. This is right. I mean, this is the saddle point. No interaction here taken into account yet. And it turns out, not without surprise, that we arrived at this point also in our 2PI description. So what we have, and now, okay, and now I'm again running out of board. Yep.
We're taking derivatives respect to S or like S to
This guy,
yes.
full S, but evaluated at the saddle point. And it's the same terms You can plug it in yourself. It's gonna give me that. Okay, so what do I have now? I have d5 I delta S2 is going to be equal to the path integral over minus dt prime phi g0 minus IR phi. Gaussian integrals, what's the result?
Where we both.
Close. There is a determinant there.
Yeah.
So the inverse of the determinant.
It's going to be inverse of the determinant, exactly. So it's determinant of g0 minus 1 minus IR inverse. And now I can what I have inside the 2pi action is minus I logarithm of this guy. Okay. And then there was a minus sign plus. You can check this property yourself. I'm not going to be deriving it, but logarithm of a determinant is a trace of a logarithm. Makes sense? That the logarithm of a product, determinant is like a product of a diagonal.
Yeah.
Trace is like a sum of logarithm trace sum, right? Exactly. So it's going to be I trace logarithm I R. Okay, so finally, and that's going to be the last thing we're going to do before break, we arrive at the form of the action. And, again, I'm rewriting this 2pi action just for you to know which stage are we at, okay? So I'm just massaging this expression. We are at the stage of I trace logarithm this is not there, right? Logarithm minus trace RG. What shouldn't you like about this expression? Why we still don't like this expression?
That G inverse is going to be very hard to find.
This guy?
Yes.
Oh, this guy is nice. This guy just comes from the action. This guy is a good guy. Who don't we like? Trace? No, I think Trace we're also reasonably happy about.
Just guess.
I mean, okay, there's also a finite number.
I don't.
The only thing left is R or the action itself.
Here, someone buy this man a beer.
You're
R, we don't like R. What the hell is R, right? This was just like a thing which was supposed to help us in computations. We're supposed to actually eliminate R. So after the break, we're gonna deal with R. And now coffee.
Just like we keep trying till we got it by